Let's do this, shall we? Yes, we shall. It's going to be glorious. It's always glorious. Glorious gloriosity. Yes. All right, so reminder that we were talking about apparent magnitudes, that they're this logarithmic brightness scale where 5 magnitudes difference is a factor of 100 in brightness, and 1 magnitude then is a factor of the 5th root of 100, or in other words of about 2.512. And we said that it's upside down, that smaller magnitudes are brighter instead of, well, what we should have done, but we stuck with history. Astronomers have this tendency to have these anachronisms that we then just get stuck with. So my job is to help, instill those anachronisms in you as well, to continue the tradition. So we said that there's 2 versions where if we knew the 2 magnitudes, then we could say that the ratio of the fluxes from the 2 sources, maybe it's 2 stars, probably is, 10 to the minus 0.4 m2 minus m1, where m1 and m2 are the 2 magnitudes involved. Or if we knew the flux ratio, we can turn that around and say that m2 minus m1, the difference in the magnitudes, is 2.5 times the base 10 logarithm of the flux ratio, F2 divided by F1. And we also mentioned that, notice that all we have here is everything's in terms of the difference in the magnitudes. We haven't said how we would figure out what any one particular magnitude was. And so in other words, this scale has to be calibrated. What you have to do is pick stars and assign magnitudes to them. And we'll talk a bit more about that later. But do keep that in mind, is that so far this is all just about differences in magnitudes. And you need to say, okay, well, what brightness corresponds to magnitude 0? And it turns out that while in principle you could just say a certain flux corresponds to magnitude 0, it's actually hard to precisely measure fluxes because of various variations in instrumentation. And so what we do in practice is we pick some standard stars and assign magnitudes to them based on finding ratios of their brightnesses and so forth. Anyway, what questions do you have at this point? All right, so we've been talking about apparent magnitudes. We've been talking about how bright things look to us. But on the other hand, we know that how bright a star looks to us depends not only on how much light it's giving off every second, how much light energy it's giving off every second, but also on how far away it is. And so we also talk about what are called absolute magnitudes, which are a measure of a star's quote-unquote true brightness, or in other words, of its luminosity. So absolute magnitudes. A star's absolute magnitude, as opposed to its apparent magnitude, its absolute magnitude is defined to be the apparent magnitude it would have if it were at a standard distance of 10 parsecs. It's the apparent magnitude that it would have if it were at a standard distance of 10 parsecs. Standard distance of d equals 10 parsecs. In other words, about 32.6 light years away from us. So, of course, the way that we can measure a star's absolute magnitude is get into a spaceship and fly until we're 10 parsecs away from it, measure its apparent magnitude, and report back. Or we can do a calculation and show how the apparent and absolute magnitudes were related, because you all were not looking at me like you're out of your mind when I was saying all of that, right? No, we can't do that. We don't have that technology. So, but the math tells us what to do here. So, stars, apparent magnitude, which we'll call little m, how bright it looks in our sky, little m, and its absolute magnitude. What am I going to use for absolute magnitude? If little m is the apparent magnitude, guess what we'll call the absolute magnitude? Big M, as a matter of fact, yeah. And its absolute magnitude big M are related by I'll move it over here. So what we'll say here is go back to this relationship right here, and we will call F sub 10 the flux that we observe from the star 10 parsecs away, what we would observe if the star were 10 parsecs away, and we'll call F the actual flux that we observe from the star here on Earth. So we'll say that the flux ratio, F10 divided by F, right? So it'll be flux at 10 parsecs away from the star, and F there will be actual flux at Earth. Well, we'll just use this magnitude relation right here. In other words, it'll be 10 to the minus 0.4 equals 10 to the minus 0.4 from the definition of the magnitude scale. So what's playing the role of M2? What's playing the role of M1? Is it the absolute magnitude or the apparent magnitude? Is it big M or little m that we're going to put in here for M2 and M1? So we've got F10 on the top. So what is going to, I've got this working backwards in my head here. Let's see, I think I want to, because I've got it a little bit differently in my notes. So let me think about this so I don't mess it up here. So F10, so I think, it's all right. I can make it work either way. So, yeah, okay. So actually, I'm gonna flip this over because I want it to look in the usual way. So I'm going to put it. So the flux. How do I want to do this? I should have just rewritten it in my notes here to make it go the way I want it here. Yeah, I'm gonna make it this. F over F10, okay, is 10 to the minus 0.4, so which one goes here? Is this little m or big M? It's little m, right, because I've got it putting in the same order. Little m minus big M, right? Right, so in other words, I'm letting little m play the role of M2 here, so the one that is on the top, and big M is playing the role of M1, the one that's on the bottom, right? Okay. And this will be equal to, from the inverse square law, it will be equal to and then I got to get this right here, it'll be equal to 10 parsecs divided by the actual distance to the star squared from the inverse square law. From inverse square law, right? Because what does the inverse square law say? The inverse square law said that the flux is equal to what? Yes?
Is it luminosity over 4 pi r squared?
4 pi r squared, right? So the luminosity over here, we'll call it 4 pi d squared, because we're saying the star is a distance d away from us, since I called it r before, so here it'll be d squared. So the flux is the luminosity, total energy per second the star is emitting, divided by 4 pi d squared, the area of the giant sphere of radius distance over which the flux has been spread out. Yes?
Should we flip those notations?
Which notations?
Actual flux at Earth and the electrical.
Oh, well, yeah, I flipped it around. You're absolutely right about that. Thank you for pointing that out. So, okay, now it looks ridiculous. But yeah, those have to be flipped around. You're absolutely right about that. Yes. Okay, so this says that F2 over F1 is equal to L2 over 4 pi D2 squared divided by L1 over 4 pi D1 squared, right? So in other words, cancel, 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 you get D1 over D2 squared, right? So another way of writing the inverse square law is to say that the flux ratio and the distance ratio are related in this way, that the flux ratio is the inverse of the distance ratio squared. That's another way to put the inverse square law. Does that make sense? What questions do you have? I'm not seeing people saying, yeah, that makes sense. I'm seeing people looking puzzled.
Why don't we write F and F sub 1 there?
I could, right here. So first of all, right, be sure you understand that what I'm doing right here is that this is L2 over 4 pi D2 squared. I'm dividing by L1 over 4 pi D1 squared, which means I'm multiplying by what? If I divide by L1 over 4 pi D1 squared, that's the same as multiplying by 4 pi D1 squared over L1, right? And so this is, yeah, I forgot something here. Maybe that's why you're looking at like you're not buying what I'm selling here. I meant to say the same L's here. This is for F2 over F1 for the same star at two different distances. So I was not quite right here unless I make the two L's equal to one another so that they will in fact cancel. So in other words, what I'm saying here is, here's the flux from the same star at distance d2 divided by the flux from the same star at distance d1. Same star seen at two different distances. So that'll be L over 4 pi d2 squared over L over 4 pi d1 squared, which is the same as L over 4 pi d2 squared times 4 pi d1 squared over L. So the L's cancel, the 4 pi's cancel, and you get d1 squared over d2 squared, which is the same thing as d1 over d2, the quantity squared. Yes?
Sorry, but I'm not understanding how that equation relates to that one.
So now just say F10 over F, or I'm putting it the other way, F over F10, right, is equal to, in this case, you would say it's like, okay, D10 over D, the quantity squared, but by D10 here, right, the distance, I mean 10 parsecs, because that's the distance that I'm standardizing on. So this will be 10 parsecs divided by the actual distance squared, because I'm comparing the star at distance D from us, and at distance 10 parsecs from us. So if I call that other distance d10 as opposed to d2 or whatever, right, then it's 10 parsecs that I put in for one of the distances that I'm looking at, where the flux is F10, and d for its actual distance away from us, where the flux is F. Does that make sense?
Yeah.
That's what we're getting at here. So this is, yes, go ahead.
Sorry.
Yeah.
Does that equal what's behind you, d1 squared over d squared?
It does in this case, because in other words, I'm calling, in this case, d1 10 parsecs. I had right, d1 is 10 parsecs, d2 is d in this case. Yeah, right. Yeah, so this is just, if I call d1 10 parsecs and d2 d, and then the fluxes correspondingly, it's just a special case of that more general relationship. Yes. So what we're doing here is saying, okay, here's the definition of the magnitude scale applied to the flux ratio, and here is the inverse square law applied to the flux ratio. This equals sign from the magnitude scale definition, this equals sign from the inverse square law. Okay? Happy? Not happy? Shall we continue? Okay. So, of course, so this would be one way to put it, or we can do the inverse of this. We can rewrite this as little m minus big M is equal to 5 times the base 10 logarithm of the distance divided by 10 parsecs. And from the way people are looking today, I feel like I should just make the math explicit again. So if I wanted to invert this, right, what would be my first step to solve for little m minus big M here? What would I do to both sides first? Take the logarithm, right? So I take the logarithm, so that says base 10 logarithm of f over f10 would be equal to minus 0.4 little m minus big M, right, equals, what happens when I take this logarithm? Equals the base 10 logarithm of d over 10 parsecs squared. What happens here when I take this logarithm? So the logarithm of x to the power of y is equal to what? Y log x, right? Y log x. So this is 2 times the logarithm of d of 10 parsecs over d. Sorry, 10 parsecs over d. 10 parsecs over d. Right? Which is the same as, what if I wanted to make it logarithm of d over 10 parsecs? What if I wanted to flip that around like I've got it there? What do I change? I have a minus sign. This is minus 2 times the logarithm of d over 10 parsecs, because 10 parsecs over d is to the power of minus 1 is d over 10 parsecs, right? So the base 10 logarithm of d over 10 parsecs is minus 1 times the base 10 logarithm of 10 parsecs over d. Now I have to keep them from colliding with one another, right? And so now I can solve for little m minus big M here. Little m minus big M is going to be minus 2 divided by minus 0.4 of the logarithm of d over 10 parsecs. But what is minus 2 divided by minus 0.4? It's 5, right? That's just 5. So you get, as advertised, little m minus big M is 5 times the base 10 logarithm of d over 10 parsecs. So this is worth drawing a box around. Little m minus big M is 5 times the base 10 logarithm of the distance over 10 parsecs. But we can also write it in a more commonly used form, which is, what's another way to write the logarithm of d over 10 parsecs as a subtraction, as a difference? What would I do?
Oh, log to the base 10 d minus log to the base 10.
Yeah, this would be 5 log to the base 10 of d minus 5 log to the base 10 of 10. We'll ignore the units here for these purposes. You tend to do that when you use logarithms because there's really no such thing as a logarithm of a parsec, so it works out mathematically unit-wise. It's a little fishy, but whatever. What's the base 10 logarithm of 10? 1, because 10 to what power is 10, right? The logarithm of a number, base 10, is the number to which 10 must be raised to give that number. Quick! To what power must 10 be raised to give 10? The first power, right? So in other words, this is 5 log d minus 5. And so you often also see this as little m minus big M is 5 times the base 10 logarithm of d minus 5, where it's understood that d is in what units? It's understood that d is. What's that?
Is it still parsecs?
It's still parsecs, that's right. D is in parsecs here. That's right, yes, D is in parsecs. D is in parsecs. This is the one that you most commonly see is little m minus big M is 5 log d minus 5, and little m minus big M, the difference between the apparent and absolute magnitudes, is called the distance modulus. Because it's related to the distance. So little m minus big M is 5 log d minus 5. And so this tells you, okay, if I know the distance to the star and I know its apparent magnitude, I can just solve for capital M to find its absolute magnitude. So that's how you find actual absolute magnitudes for stars, is if you can use parallax to find its distance and you've measured its apparent magnitude, this allows you to calculate its absolute magnitude, what its apparent magnitude would be if it were 10 parsecs away. What does this simplify? Check. What does this simplify? If d is 10 parsecs, what's the logarithm of the distance if d is 10 parsecs? 1. So what is 5 log d minus 5? 0. So how are little m and big M related according to this? What's their difference in that situation? 0. They're the same as they should be because big M is little m when the distance is 10 parsecs. So this is entirely consistent with that. Plug in 10 parsecs, you get that little m and big M are equal to one another. And we can solve this for D. What if I know the apparent magnitude and the absolute magnitude and I want to know the distance? So how would I solve this for D? If I just start with this and solve it for D, what would I do? What's my first step? To get rid of that logarithm right there. Everything gets raised to the 10 power, right? So 10 to the power of little m minus big M is equal to 10 to the power of 5 log 10d minus 5. Okay, so now what do I do? If I have 10 to the a plus b, how can I write that as a product? 10 to the a, 10 to the b, right? 10 to the a, 10 to the b. So this is 10 to the 5 log 10d times 10 to the, what am I doing here? I want this to be right. Oh, actually, no, that's this. Should read further in my notes. What I was saying wasn't wrong, but what I want to start with is, okay, 5 log 10d, I was being silly there. 5 log 10d is little m minus big M plus 5, right? Okay, so then log 10d, in other words, let's first solve for log 10d and then raise everything to the power of 10. So log 10d is little m minus big M plus 5 divided by 5. Now take 10 to the power of both sides. 10 to the log 10d is equal to 10 to the power of little m minus big M plus 5 divided by 5. Quick, what's 10 to the log 10d? What's 10 to the logarithm base 10 of d?
Would be D.
Just d itself, right? Right. 10 to the logarithm of a number is the number, right? Because those are inverse operations. So in other words, if I know little m and big M, here's how I find the distance. Take 10 to the power of little m minus big M plus 5 divided by 5. And that'll be in parsecs when you do that. Because absolute magnitudes are calibrated to distances in parsecs. So if a star is less than 10 parsecs away, will its absolute magnitude be more than its apparent magnitude or less than its apparent magnitude? Let's see, if it's less than 10 parsecs away, does it look brighter than it would at 10 parsecs or dimmer than it would at 10 parsecs? Brighter. And on the magnitude scale, which way does it go? Are dimmer magnitudes brighter? Are brighter magnitudes smaller numbers or bigger numbers? Smaller. So if the star is closer to us than 10 parsecs, its absolute magnitude is smaller than its apparent magnitude because it would look brighter than it would at 10 parsecs, and vice versa. If a star is more than 10 parsecs away from us, then its absolute magnitude is larger than its apparent magnitude because it looks dimmer than it would at 10 parsecs, and dimmer is bigger, right, when it comes to magnitudes. For the sun, it depends on the filter, but if you look at what's called the bolometric magnitude, integrated overall wavelengths, the apparent magnitude of the sun. And so we use a circle with a dot inside as a very standard symbol to mean the sun in astronomy. In LaTeX, that would be if I wanted to create that, it would be M underscore O dot, like that in LaTeX. Slash O dot, backslash O dot is that circle dot symbol in LaTeX. So, and we have to be careful because this looks dangerously like a symbol for mass too, and so you have to know the context here. The apparent magnitude of the sun is minus 26.81. And the absolute magnitude of the sun, so this is often used to mean the mass of the sun as well, capital M, circle dot like that. So in fact, that's dangerous. I'll just go like this. But you could, but I'm just saying be careful with the context, whether it's mass or magnitude, is plus 4.76. And that's because the sun is way, 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 way less than 10 parsecs away from us. So there's a huge difference between its apparent and absolute magnitudes. In terms of, so first of all, what questions do you have? So in the homework that I just posted, you'll get an opportunity to practice with these things. Yes?
So wait, what does the magnitude of 0 look like? Would that just be...
So we have to decide what a magnitude of 0 looks like. Yes, so according to us, right? So astronomers had to decide what to call a magnitude of 0. So first of all, let's look at some magnitudes of some common things that we see in the sky. And I'll tell you that, are you familiar with the star Vega? Vega is very nearly defined to have magnitude 0 through every filter. We'll talk about filter magnitudes later today. It's very nearly defined to have magnitude 0 through every filter, through the B filter, through the V filter, through every filter. We actually, because we don't want to tie it to a single star, there's what's called the North Polar sequence of other A spectral type stars, capital A spectral type, because they look fairly white to our eyes, and so it was arbitrarily decided to just say, well, you know, white's a blend of all the colors, and so call this bright white star magnitude 0. Now, it's actually not quite that because of bringing in other stars as well, but through the visual, the V filter, for example, Vega's magnitude is plus 0.02. So if you want a sense of what does a 0th magnitude star look like, Vega's your star. 0th magnitude is Vega. Is Vega the brightest star in the sky? It is not. What's the brightest star in the sky other than the sun? Sirius, right? So if it's brighter than magnitude 0, its magnitude number, has to be less than 0. It's negative. So that's showing here, right? Sirius, the brightest star in the night sky, magnitude minus 1.4 for its apparent magnitude. The brightest thing in the sky besides the sun and the moon is the planet Venus. When it's at its brightest, its magnitude minus 4.4. A full moon, minus 12.6. The sun, it's giving it as minus 26.7. I said minus 26.81. It depends on the filter that you use, or if you're using a filter and so forth. So I think that's for the V filter that's given there. I'm not sure exactly, but in any case, don't worry about that slight difference. So that is spectacularly brighter, obviously, than anything else in our sky. It's something like 100 billion times brighter than Sirius is to us, something like that. Again, that's why we use a logarithmic scale for magnitudes, because it compresses the numerical range down. The naked eye limit under really dark skies and really good eyes is about plus 6.0. It's set up to correspond to Hipparchus saying that the dimmest stars he could see with his eyes under the unpolluted night skies of ancient Greece were 6th magnitude stars. Through binoculars, you can see dimmer than that. You can get down to a magnitude of about plus 10.0 visually through binoculars. There are spectacularly more stars visible through binoculars than there are to the naked eye. We only see a small fraction of the stars in our sky because our eyes have relatively small apertures and our retinas aren't super duper duper sensitive. Pluto's magnitude is plus 15.1. If you look through a very large mountaintop telescope with your eyes, you can see down to about magnitude plus 21. Through the Perkins telescope, visually, I've seen things that are like 16th, 17th magnitude, something like that. The Hubble Space Telescope and Large Earth Space Telescopes with long time exposures can see down to like magnitude plus 30 or something like that. To give you a sense of some other stellar magnitudes, so y'all are familiar with the Big Dipper, right? The stars in the Big Dipper are roughly magnitude 2. They are 2nd magnitude stars. And do you know that the middle star in the Big Dipper's handle is actually 2 stars to the naked eye, if you look very carefully? Are you folks aware of that? Or not? So, okay, I feel like I should bring up stellarium here and kind of illustrate that. And the next time you see the Big Dipper, I want you to look at the middle star in the handle and notice that it's actually 2 stars, the brighter of which is called Mizar, and the dimmer of which is called Alcor. Alcor, the dimmer one, which is just a little above it, is a 4th magnitude star. Its magnitude is just about 4.0. Under the skies of Delaware, even at Perkins Observatory, it's not super easy to see, but you should be able to see it if you have good eyes. At our skies, maybe you can get down to like magnitude 4.5 or something like that before the light pollution makes it really hard to see dimmer things than that. So if you go to dark skies, you see down to magnitude 6.0, you see many, many dim stars that you can't see under light-polluted suburban skies, which is part of what makes going to a truly dark sky site quite the spectacular experience if you're not used to it. Well, even if you are used to it. Let me get my, where's the cursor? Come on, where's the cursor? There it is. Okay, let me click here. So this is the Stellarium Free Sky Simulator. If you've never downloaded it before, go to stellarium.org and download it. You can also put it on your phone. It's a somewhat different version, but you can use it to hold it up to the sky and know what you're looking at. So let me change the time to after sunset here. Doink, 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 doink. Let me turn off the lights because we have a lot of light pollution in here, so to speak. Okay. Doink. Ooh. And here we go. Let's turn around to the north here. And so like here's Antares and Scorpius, and if you click on it, we can see that its absolute magnitude is minus 5.10, but its apparent magnitude is 1.05, for example. So that's a 1st magnitude star. And there's Arcturus. And here is the Big Dipper, and I'll click on, if I get it right, there's Mizar, magnitude 2.20. And let's see how well I can zoom here. Can I pinch with this? Let's see, because I don't have a mouse connected to this, so it's going to make it harder for me to zoom in. How do I zoom in with this without a mouse? But anyway, this star right here, even with this, I think if you look carefully above it, you can see a little nub in there, and with your eyes, you'll actually see a separate star there. That is Alcor, and if I can hit that one, Mizar and Alcor. Okay, so it's just doing them both together, but okay, maybe I can get a mouse later, but Alcor is right about 4th magnitude. So that can give you kind of a sense of magnitudes of stars that you can see in the night sky, roughly speaking. That's apparent magnitudes. And then absolute magnitudes can be, of course, very different from that because of the fact that they're at different distances from us. When you look at the night sky, you're getting a very biased view of what's out there. When you look at the night sky, if you look at the types of the stars that you're seeing, giants and supergiants are overrepresented compared to their actual numbers. Why would that be? Why do we see many more giants and supergiants in the night sky compared to the fraction of giants and supergiants that are actually out there amongst stars? Why would that be? Yes?
Is it because they're brighter and easier to see?
Yeah, because they're much more luminous, and as a result, we can see them to much further distances. So the sun's absolute magnitude is 4.76. That means that if it were 10 parsecs away, about 32.6 light years away, it would be considerably dimmer than Alcor is, which is not that easy to see. 4.76 would be very difficult to see in the skies of Delaware, Ohio, even at Perkins Observatory. 10 parsecs isn't that far away as far as stars go. On the other hand, Betelgeuse in Orion is like magnitude, I think it's 0, well, it's roughly 0, it might be minus 0.5 or plus 0.5 or something like that, but it's quite a bright star, and it's like 600 light years away. It's much further away than that. We can see giants and supergiants to much bigger distances than we can see more ordinary stars like the sun. The most common type of star in the universe is M dwarfs, and they're like 90% of the stars in the universe. Not a single one is visible to the naked eye. The nearest star to us is Proxima Centauri and M dwarf. It's not visible to the naked eye because they're so dim. The sun, we often hear, it's an average star. It's not. It's more massive and more luminous than about 90% of the stars in the universe. It's like in the 90th percentile. But there are giants and supergiants that are spectacularly more luminous than the sun, and because of that, even though they're very rare, only a tiny fraction of stars are supergiants and giants, they dominate what we see in the night sky because we can see them from so far away. Yes? Do you have a comment or question?
I did.
Okay. Oh, I just kept talking and made you forget your question. It's terrible. Sorry. Yeah.
Oh, yeah.
Yeah.
So, like, supergiants and giants and stuff like that, are they actually, like, more luminous per, like, square foot of surface or whatever?
No, not necessarily.
It's really big.
Yeah, they're just big, right? So, for example, consider red giant stars, right? They have lower surface temperatures than the sun do. That's why they have that reddish color, which means that they are giving off less radiation per square meter of their surfaces than the sun is. However, when the sun is a red giant, it's going to be about 100 times bigger across than it is now, which means that its surface area will be something like 10,000 times larger than it is now. And its luminosity, when it peaks, will be about 2,000 times larger than it is now. Notice that's smaller than the surface area ratio. If it were just as bright per square meter, then it would be like 10,000 times more luminous as now. It would only be 2,000 times as luminous because its surface temperature will be lower. So there'll be less light coming out of each square meter, but it will more than make up for that in having so many frickin' square meters that are sending out light. Yeah. Mm-hmm. Yep. Okay. Yeah. All right. So, have I done the thermal radiation demo for you folks? Maybe for some of you, where I crank up a light bulb and stuff like that. How many of you have seen that demo, cranking up a light bulb? Okay, better yet, how many of you have not seen the demo? Some of you have not. This is what I need to know. If you've all seen it, why bother doing it again? Some of you have not, so let me go grab it. we have here a light bulb. Ooh. Ah, it is an old-fashioned light bulb. It has a filament. That means it is a light bulb where it starts with an I. It's an light bulb. What is incandescent light bulb. So I'm going to plug it into my variac here, which allows me to vary the voltage across the filament between 0 and 140 volts. So, let's make the light go down. Don't know how well this will translate to the video, but we'll turn off the lights. Oh, they're already off, right? These are the ones that need to turn off. Hi. All right, so I'm going to start cranking up the voltage, therefore increasing the current through the filament, therefore increasing its temperature. So I want you to tell me, especially if you haven't seen the demo before, I'm going to say there's two things happening to the light coming from the filament. So I'm cranking it more and more and more and more and more and more, and this is only a 25-watt bulb, which isn't much for an incandescent bulb. A 25-watt LED bulb would really be like, but in any case, what are the two things that are happening to the light as I increase the temperature? It is getting brighter for sure. Yeah, it's getting brighter. What else is it doing? It's changing color. It's changing color. Yes. So from the halcyon days of physics 280, when you studied thermal radiation, also called blackbody radiation, I'm going to presume that you studied the all on. Well, they've really simplified this thing. There's got to be better than that. Anyway, it's all off and all on. It's digital. Two radiation laws describe what's going on. Which one describes that it is changing color? Do you remember? The gentleman's name starts with a W. And if you are in Austria, it's how you say the name of your capital city. What's the capital of Austria? It's Wienslaw. It is Wienslaw. Yes, it is Wienslaw. In Austria, the capital is Wien. We say Vienna, but they say Wien. So that's Wienslaw. And then two folks have their names attached to the description that the radiation gets brighter. Who are those two people? S and B. S is Stefan, and B is Ludwig Boltzmann. Yes. So Wien's law describes the changing color, and the Stefan Boltzmann law describes the fact that it gets brighter and brighter. Why, let's take a break and then dive into those, shall we? Yeah. Yes, we shall. Yes. Woohoo! Or we'll take a really long break and go to the video. Yes, in some people's cases. All right, back to it here. Let's see. Can I assume y'all know what a quote-unquote black body is, right? You had that in 280. So you've seen the thermal radiation laws before, and we're just reviewing them here. But definitely let's do that. So remember that a black body, quote unquote, is an ideal emitter and absorber of radiation. And by that we mean that it absorbs what fraction of the radiation, the electromagnetic radiation. Remember, light is just one form of electromagnetic radiation, characterized by, or at least visible light, characterized by the range of wavelengths that our eyes can see. What range of wavelengths can our eyes see? 400 nanometers to 700. Yeah, 400 nanometers to 700 nanometers. We perceive different wavelengths as having different, what? Visually, how do different wavelengths look to you? Different colors, right? So we have the colors of the rainbow, which are Red, orange, yellow, green, blue,
Indigo.
violet, right? Yes. I don't believe in indigo. It's bluish purple, damn it. Yes?
When I was in 5th grade, I argued with my teacher that indigo wasn't like a legit color out there.
Yeah.
I kept getting
How'd it
my
go?
homework for it.
Did you really? Yeah. Give me their name. I mean, it's kind of arbitrary, obviously, right? But to me, you know, indigo, chartreuse, right? You know, it's like, it's a J. Crew color. It's there to make Roy G. Biv, the mnemonic, easier to say, in my not very humble opinion. Which end is the violet end? Is that the 400 or 700 nanometer end?
701.
No, it's the 400 nanometer end, right? Violet is the short wavelength end, red is the long wavelength end. So Roy G. Biv goes from 700 down to 400 nanometers. But also keep in mind that the colors of the rainbow are not all the colors. For example, this yellow right here, this is not a wavelength of yellow light that you're seeing. It's a whole range of wavelengths that are blending together to make this yellow color. The colors of the rainbow are pure colors, analogous to pure tones in sound, where you hear just a single frequency. But you know, why do people's voices sound different even if they're singing the same note? Because their vocal cords and the cavities in their head have different resonance patterns, and so the blends of the harmonics are different for different people, which is why everybody's voice sounds different from one another. Anyway, so if we want to say what a black body is, it's a quote-unquote perfect emitter and absorber of radiation. Meaning it absorbs what fraction of the light that falls on it. If it's a true, perfect, quote-unquote black body, what fraction of the light does it absorb that falls on it? 100%, all of it. It absorbs 100% of the radiation falling on it. Does anything actually do that? No, it's an idealization. Anybody know what the closest, if last I heard, the closest thing we have to that? Have you ever heard of it before? This Vanta black is this, I guess you could call it like a pigment or substance or whatever, and it absorbs, like, question or comment.
Hole is also a black body, right?
What's that?
A black hole is also a black body.
Well, yeah, pretty much, except that it emits a, well, I guess you could say, yeah, I wasn't thinking in those terms. Yeah, it'll pretty much absorb any radiation that falls on it. So, okay, fair, yeah. But we can't bring them to the laboratory. Damn it, I know, yeah. So outside of that, we'll have to deal with Vanta black, which is like 99 point something, something, something. And I'd like to see some of it sometime. I mean, even in pictures, it looks really, really black. And I mean, of course, that ain't doing it. But wow, your shirt's got pretty black stripes on there, actually. Still not Vanta black, though. So in other words, that's why we called it a black body, because if it's not hot enough to glow on its own, it would look as black could be, because it was just eating every photon that fell on it. So are my shoes outside of the red stuff black? Yes. Are they black body black? No, because you can see texture, you can see structure on them and so forth. There's at least some light being reflected. So it's an idealization. It absorbs 100% of the radiation falling on it and emits radiation with a characteristic spectrum that depends only on its temperature. depends only on its temperature. Only on its temperature. And kind of big picture, as opposed to fine details. Big picture radiation laws. Why, we have Wien's law, which says that lambda max T is 2.90 times 10 to the 6th nanometer Kelvin, or if you like, 0.0029 meter Kelvin. So lambda will be in distance units. If you express it in meters and the temperature is in Kelvin, then lambda max T is 0.0029 meter Kelvin. Switch to nanometers, multiplied by a billion, to account for the fact that a nanometer is just a billionth of a meter. You get 2.90 times 10 to the 6th nanometer Kelvin, which is usually the one to be more useful for us. So it emits radiation with a characteristic spectrum. We will give the mathematical form of the spectrum momentarily, but here are blackbody curves, spectra, for various temperatures, 3,000 Kelvin, 6,000 Kelvin, 12,000 Kelvin, which are kind of a range of stars could have those kinds of temperatures. 3,000 Kelvin would be a very cool star. What's the surface temperature of the sun, do you know? It's about 5,800 Kelvin, 5,770 Kelvin, so not too far off of a 6,000 Kelvin temperature. Stars are roughly black bodies with the radiation they give off, certainly not precisely. They have spectral lines, they're not smooth curves. It doesn't quite follow a black body curve, but roughly they can be described with black body curves. And lambda max, also called lambda peak, is just where this curve reaches its maximum value. So for 3,000 Kelvin, the maximum value is at about 1,000 nanometers. For 6,000, it would be at half that, right? Because if you flip this around, or you solve for lambda max, you get 2.9 times 10 to the 6th nanometer Kelvin, divided by the temperature in Kelvin. So if it were 2,900 Kelvin, then lambda max would be at what wavelength in nanometers? If the temperature were 2,900 Kelvin, 2.9 times 10 to the 3 Kelvin, what would lambda max be in that case? What's 2.9 10 to the 6 over 2.9 10 to the 3, 2,900? 1,000, that would be 1,000 nanometers. So a 2,900 Kelvin black body, close to this, would peak at 1,000 nanometers. So that's, this is just about accurate there. If you double the temperature, what happens to lambda max? It becomes only what as large? Half as big, right? Because it's 1 over T, right? Double the temperature, half as large. So at 5,800 Kelvin, like for the sun, good approximation, what should lambda max be at 5,800 Kelvin? If it's 1,000 nanometers at 2,900 Kelvin, what's it at 5,800 Kelvin? 500 nanometers. The sun's thermal radiation, expressed per unit wavelength interval, peaks at about 500 nanometers. Is that in the visible spectrum? Yes, it is, because the visible spectrum is 400 to 700 nanometers. Is that a coincidence that the sun's thermal radiation peaks in the part of the spectrum that our eyes are sensitive to, or do you think there might be some explanation for that? And if so, what would that explanation be? Biologically speaking.
I mean, it better be visible.
Because if you're an animal that wants to survive and have offspring, does it help if your genetic makeup is such that your eyes are sensitive to the light that your star likes to give off? Yes, it does. So there's good evolutionary reason for the fact that our eyes are sensitive to the light that the sun gives off. Our eyes are most sensitive at something like 550 nanometers. It matches nicely with where the sun likes to give off radiation. Not a coincidence, that's evolution in action. 12,000 Kelvin, or double 5,800, so 11,600 Kelvin, the peak would be at what wavelength? If I double the temperature again, it was 500 nanometers for 5,800 Kelvin. What's it going to be for double that? 250 nanometers. Is that in the visible part of the spectrum? No, it is not. What part of the spectrum is that? If we're a bit short of the visible, that's the ultraviolet. So a 12,000 Kelvin star, or thereabouts, its light peaks in the ultraviolet when expressed per unit wavelength. Its curve peaks in the ultraviolet. Does that mean it's not visible to us? Is it giving off visible light? It certainly is, right? It certainly is. Is it, from the graph here, is it in a sense giving off more short wavelength light or long wavelength light? Short wavelength light. So what color should such a star be? It should be more biased towards shorter wavelengths. So what colors are going to look? Yeah, like bluish white, right? On the other hand, the 3,000 Kelvin star here, the peak is in the, not the visible, but the infrared, but is it giving off visible light? Oh yeah, look, the curve is certainly not zero within the visible range. Is it giving off more long wavelength or short wavelength photons? Longer wavelengths, right? So what color should it look? Like reddish or orangish, basically, right? Whereas the sun peaks with kind of, right within the visible range in the middle somewhere, and that's why the sun looks white. No, it doesn't. You say it looks yellow. Well, apparently, if you're in space, it looks white to people. So why does every kid draw the sun yellow? Why do we think the sun is yellow? Because we tend to see it at sunrise and sunset, where a lot of the shorter wavelength light is scattered out more by the atmosphere because of the longer path through the atmosphere, which tends to make it look yellower than it really is. And apparently that's why we think the sun is yellow, but it's actually pretty darn pure white if you were to view it from above the atmosphere and not with blinding, If you put a very strong neutral density filter, that passes all colors equally well above the atmosphere, the sun looks white, essentially. So Wien's law says that the peak in the radiation spectrum shifts to shorter and shorter wavelengths as the temperature increases, and it's changing color as a result of that for exactly the reasons we were just talking about, right? The mix of wavelengths within the visible part of the spectrum that you see changes with the temperature. At very high temperatures, it's more biased towards the short wavelength blue, green, violet end, and our eyes have blue receptors in them, and so they look bluish or bluish white to us. Cool stars look reddish orange to us. And in between, you get yellowish to whitish to bluish whitish, essentially. No star looks green. The sun, the sun's peak wavelength of 500 nanometers, if you just shine that light, it looks green. That doesn't mean the sun's going to look green because it's got all the other wavelengths too, and they blend to a whitish appearance to our eyes. Okay, so that's Wien's law. Everybody happy with Wien's law? Woohoo! Okay, now let's do the Stefan Boltzmann law. The Stefan Boltzmann law. right? And by the way, Wien's law. Cool stars are red, hot stars are blue. Oh my, I've started a little nursery rhyme or whatever. So, I love astrophysics, and so do you. There we go. So that's our verbal description of Wien's law, sort of, kind of there. All right, yes. Isn't that lovely? Okay. Stefan Boltzmann law. I'll just make it simpler. Hotter is brighter. Actually, lot brighter, because the Stefan Boltzmann law says F equals sigma T to the 4th power, T being the Kelvin temperature. It's Kelvin temperature over there too. Kelvin, stop it. Kelvin temperature. What's absolute zero on the Kelvin scale? What Kelvin temperature corresponds to a temperature of absolute zero? Yeah, zero. It's zero. You're thinking of Celsius, right? Minus 273.16 Celsius or whatever. But Kelvin, so how does a Kelvin compare to a degree Celsius in size?
Aren't they 1-to-1?
They're 1-to-1. They're exactly the same size. They're just shifted. The Kelvin scale starts at absolute zero, whereas the Celsius scale starts at nominally, the freezing point of water, so to speak, being 0 Celsius. But other than that, they're the same. So if you think about it then, let's see, so roughly what is the temperature of this room in Celsius? About 20-ish or thereabouts. 20 Celsius is exactly 68 Fahrenheit. Because the Fahrenheit scale is now defined in terms of the Celsius scale, where 5 Celsius degrees is 9 Fahrenheit degrees exactly by definition. And what was I going to say? Freezing point of water on the Fahrenheit scale is nominally 32. Boiling point is 212. I mean, it depends on the atmospheric, but it's under standard temperature and pressure. It's like 32 and 212, whereas in Celsius it's 0 and 100, right? So 180 Fahrenheit degrees is 100 Celsius degrees. So therefore, 9 Fahrenheit degrees is 5 Celsius degrees, right? So as an aside here, because I can never be distracted, I've decided, and Isa approves of this, I've set all my apps and everything to Celsius now, because I want to get Celsius. My car, it's all Celsius. I'm Celsius now. And, so, but of course, Americans, right, don't seem to relate to that well. It's easier than you think. You just have to remember some touch points. So 68 Fahrenheit is 20 Celsius, and every 5 Celsius is 9 Fahrenheit. So if you remember that 68 Fahrenheit is 20 Celsius, 25 Celsius is 68 plus 9 is 77. 30 Celsius is 77 plus 9 is 86. 35 Celsius is 86 plus 9 is 95. And so on and so forth. You go downwards too the same way. And so what you do is, it's not that hard to remember those touch points, what all the 5s are on the Celsius scale. And then roughly, every Celsius is about, not quite, but is about 2 degrees Fahrenheit, right? So in other words, it's like, oh, it's going to be 17 degrees Celsius today. Do I need a jacket? Well, if you go through this, logic I was just telling you, 15 Celsius is 59 Fahrenheit. So 17 is about 4 more than that. So 17 Celsius is 63 Fahrenheit. Put your calculator away. You can just do it in your head. So just saying. So join me in the Celsius revolution, fellow Americans. I'm just saying, it's not that hard. Do you approve of my Celsius? You too. All right. Very good. Yes. Yep. And if you wanted to absolutely approve, you got to switch to Kelvin, because then it's like, you know. But all right. All right. So T is the. I'm not doing that. Yeah. What's the temperature of this room in Kelvin?
Bajillion.
A bajillion? No, it's not. So it's 20 Celsius, and what's the difference between them? It's about 273, right? Below, right? Zero, what was I going to say? Yeah. Absolute zero is like, you know, minus 273 Celsius, right? So 273 Celsius is about 0.15, whatever. 273 Celsius is, I'm sorry, Kelvin is 0 Celsius, right? 273 Kelvin is 0 Celsius. It's 20 Celsius in here, so it's like 293 Kelvin in here, something like that, roughly speaking. So in terms of your everyday life, Kelvin temperatures, 300 Kelvinish is right. Is like the regime that we're dealing with in. About 300 Kelvin is what our environment is, roughly speaking. You know, give or take 10, 20 or so forth. It certainly matters whether you use Celsius or Kelvin in that context. But when you get to like the core of the sun, the core of the sun is 15 million Kelvin. What is that in Celsius? What is it? Say again? That's not what I want to hear. It's 15 million Kelvin. In Celsius, let's see, it's a difference of around 270. But wait a minute, what precision am I giving the sun's temperature of the core to? 15 million, that's not very high precision. So I ask again, the sun's temperature is 15 million Kelvin. What's its temperature in Celsius? 15 million, right? When you get to temperatures like that, it doesn't matter whether you're using Celsius or Kelvin. Take your pick, because 300 Kelvin is a tiny fraction of a million Kelvin or whatever. So don't worry about it, right? At those kinds of temperatures. If you're talking like stellar cores, Kelvin, Celsius, it's the same for all intents and purposes. All right, back to our story. F is sigma t to the fourth, where sigma is equal to 5.67 times 10 to the minus 8th, and then the units in SI are going to be watts per square meter per Kelvin to the fourth power, because what are the units of flux? So this flux here is the surface flux. It's the power per unit area radiated. Power radiated per unit area of the surface, per unit surface area. And SI, what's the units of power? It's energy per unit time. SI energy is? Joules. Yes, it sparkles. And what is the unit area? And it's power per unit area. So power is going to be energy per unit time. What's the unit time? Seconds. So what are joules per second? Well, of course, what I really want to say is watt or joules per second, right? Yes, watts. So flux has units of watts per square meter. I'm multiplying by Kelvin to the fourth power, so sigma has to have units that turn Kelvin to the fourth power into watts per square meter. Therefore, it has units of watts per square meter per Kelvin to the fourth power in order to cancel out the Kelvin to the fourth power in the temperature, leaving just watts per square meter. So the SI units are watts per square meter per Kelvin to the fourth power. And you know what? I have this thing memorized to 3 sig figs because I can count 5.67 times 10 to the minus 8 watts per square meter per Kelvin. As a matter of fact, is the Stefan Boltzmann constant. It goes beyond that, but it's easy to memorize to that precision. So, just remember it. Okay? That is the Stefan-Boltzmann constant. Logically enough. Why? What's the name of the constant in the Stefan-Boltzmann law? In a shocking development, they decided to call it the Stefan-Boltzmann constant. Who would have ever thought of that? And yet they did. Geniuses. That makes it easy to remember what it's called. And yet they don't call 2.90 times 10 to the minus, or 10 to the 6 nanometer Kelvin. I've never heard that called like Wien's constant. Maybe it is, but I've never heard a name for that one. In the homework, you're going to joyfully derive both what I just called Wien's constant and the Stefan-Boltzmann constant by doing some enjoyable differentiations and integrations. It's going to be great. But anyway, where was I? So, stars are decent approximations to black bodies, but they're not. So here in the red is a black body curve at 5,800 Kelvin, which is close to what we would call the sun's temperature. The black is the sun's actual curve, not to very high resolution. In other words, okay, kind of, sort of, but not exactly. And because nothing is ever in perfect thermal equilibrium, giving a perfect Planck or black body spectrum, it's also called a Planck spectrum. What astronomers like to do is define what's called the effective temperature. So we define A stars, or anything else's, A stars, but let's just say stars, effective temperature via, and so this is actually a very common abbreviation, T sub EFF for effective temperature, and we literally say TEF for that. You'll hear astronomers say, what's its TEF, as short for effective temperature, give myself some more room, F by definition is sigma TEF to the 4th power. In other words, TEF is the temperature of an ideal black body that would have the same flux as the actual star does, the same power coming out of each square meter as the actual star does. So TEF equals T of a black body that would yield the same actual flux. By the way, I will mention again, black body is not the best name. It's one of these things we're stuck with. We should really come up with a better name for that, because a black body only looks black if it's not hot enough to give off any significant quantity of visible light photons. It would look black to us. But if it's hot enough, then it starts glowing, right? Stars are roughly black bodies. They certainly glow. You heat coals up, they certainly glow, even though roughly speaking they might be giving off nearly thermal radiation. Are you giving off thermal radiation? Are you glowing? Are you positively glowing? You are. Why can't you see it? It's in the infrared. That's right, it's in the infrared. And so as a result, you're not able to see it. If you run the calculations, so we'll give what the thermal radiation spectrum looks like in a minute. It doesn't go to 0 at any wavelength, no matter what the temperature is, unless the temperature is absolute 0, T equals 0 Kelvin. The theoretical curve doesn't go to 0 at any wavelength. Now, light comes in discrete packets, photons of energy, and so it's not really a smooth curve if you were counting photons. So you could make an estimate for human body temperature, about how often should your body just happen to, randomly because of thermal statistics, give off a visible light photon? And the answer is about once every 50,000 years you would happen to emit a single visible light photon, which isn't often enough for us to be seeing ourselves glowing if we turn off the lights. Okay, I think you'll agree. A star's luminosity is thus F equals 4 pi r squared sigma Tef to the 4th. 4 pi r squared sigma Tef to the 4th. Because what is 4 pi r squared? R is the star's radius. R is the star's radius. What's 4 pi r squared? That is its surface area, right? The area of a sphere is 4 pi r squared. So there's the star's surface area. What are the units of surface area? SI? Square meters. And sigma Tef to the 4th, what does that equal to? That is the, just F it. That is the star's flux. That's the flux. That's how much power is coming out of each square meter. Why? What are its units? Right? I'm sorry. Yeah. You should be looking at me funny. What should I have written here? Not F. Of the star's luminosity, what's the symbol for that? L. Yeah, L. You're supposed to call me out when I make mistakes like that. It's all your fault for letting me make that mistake and not calling me out. I did it on purpose just to see if you would. Okay, so this is the flux. Why, what are the flux's units? Watts per square meter. So if I multiply how many watts are coming out of each square meter times the number of square meters, why, that'll be the total number of what coming from the star, of watt coming from the star. It'll be the number of watts, right? That'll be the watts. So the luminosity in watts is the surface area times the flux, right? So L equals area times flux. That'll always be true. And if that area is that of a sphere, a star, 4 pi r squared, sigma Tef to the 4th. Why, that's a super fundamental relationship in astronomy. We use that sort of thing all the time when we're talking about stars. Let's look at the sun. The sun has luminosity of 3.826 times 10 to the 26th power watts. Right? So this is 383. 10 to the 26th power is 10 to the 12 times 10 to the 12 times 100. 10 to the 12 is known as a trillion, right? So 38300, if you will, trillion watts. That's a lot of light bulbs we're talking about right there. 383 trillion watts is the sun's luminosity. That's why it lets us see during the day, even though it's like 100 million miles away, 150 million kilometers away. The sun's radius. Quick, what's the sun's radius? I know you've all memorized it. What's the sun's radius? big. Yes, it is 696,000 kilometers, so about 700,000 kilometers, or we'll call that 6.96 times 10 to the 8th meters for the radius of the sun. 696 million meters, 696,000 kilometers. So if we find Tef from that formula, right, solve for Tef, that'll be L over 4 pi r squared sigma, all with the fourth root, because it's Tef to the fourth will be L over 4 pi r squared sigma. So Tef itself will be the sun's luminosity. Sun's Tef will be its luminosity over 4 pi r of the sun squared sigma. Fourth root of that, run the numbers, 5770 Kelvin. 5770 Kelvin is the sun's effective temperature, effective surface temperature, which we often just round to 5800 Kelvin. That's a number every astronomer should have at their fingertips. Sun's temperature, about 5800 Kelvin for the surface temperature of the sun. And its surface flux, the power coming out of each square meter then, is going to be F equals sigma Tef to the fourth. And if we put in those numbers, we get 6.316 times 10 to the 7th power watts per square meter, or in other words, 63 megawatts per square meter is how much the sun is giving off, about 63 megawatts per square meter. Sorry, I'm going to say 63 megawatts per square meter. Yeah, because it's a megawatts 10 to the 6 watts, right? So 63 megawatts per square meter. Stop me if I say something silly. What if I wanted that per square centimeter? Oh, look, it's a cute little square centimeter. How much coming out of each square centimeter? A square centimeter is what fraction of a square meter? What is it? A square centimeter is what fraction of a square meter? How many square centimeters in 1 square meter? You tell me. You're saying it on the video right now, aren't you? Wondering how come the students aren't just shouting it at me. I know, I feel you, okay? How many square centimeters in a meter, square meter?
100.
Hi, no, come on. No, 10,000, right? Because 100 by 100, right? Let's be careful with that, right? 100 by 100 is 10,000 square centimeters in a square meter. How many cubic centimeters in a cubic meter?
100,000?
No? A million. 10 by 10 by 10, right? There's a million cubic centimeters in a cubic meter. How much, right? Do these kinds of calculations in your head to get used to it. About what is the mass of a cubic centimeter of water? What's the mass of a cubic centimeter of water? What? Yeah, it's about a gram. That's how the gram was originally defined. So, right, cubic centimeter is about a gram. It's not the current definition, but it's close to that. So a cubic centimeter of water is a gram, okay? So if I had a cubic meter, a tank a meter by a meter by a meter, I got a cubic meter of it. How many grams? Well, wait a minute. How many cubic centimeters are in that cubic meter? 100 by 100. I meant to say 100 by 100 by 100 before, not 10 by 10 by 10. Okay, so 100 by 100 by 100 is? No, 100 times 100 times 100. How many zeros?
It's a billion.
No, a million, right? 100 times 100 times 100 is a 1 with 6 zeros, right? 1 with 2 zeros times 1 with 2 zeros times 1 with 2 zeros, 10 squared to the third. It's a million, so there's a million cc's in that tank, so that's 1,000,000 grams of water. How many kilograms of water is that? It's 1,000,000 grams, how many kilograms? A kilogram is how many grams? 1,000. So 1,000 is what fraction of a million? 1,000 times what is a million? 1,000, right? Because 1,000 times 1,000, 10 to the 3 times 10 to the 3, 10 to the 6. So how many kilograms does a cubic meter of water mass? 1,000 kilograms. What's a name for 1,000 kilograms? It's a metric ton. A cubic meter of water has a mass of about a metric ton, which is comparable to a car, basically. Right? So you ain't picking up that cubic meter of water. It weighs a metric, it's got a mass of a metric ton. It weighs about 2,200 pounds, a bit more than, you know, an English ton, so to speak, right? Okay. That was an aside, but be good at, like, you know, think of things like that, right? Be able to do those kinds of calculations in your head. I command you to be able to do those kinds of things in your head. Okay. So if it's 6.316 10 to the 7 watts for every square meter, how many for every square centimeter? Well, there's 10,000 square centimeters in a square meter, so it's going to be 1/10,000th of that number. So what do? It's 6.316 times 10 to the what? Watts per square centimeter. Yes, I'm mixing units when I'm going like SI and not SI. I don't care. It doesn't mean it doesn't make sense to say watts per square meter. Leave me alone. Just leave me the freak alone, okay? Anyway, what's my power here? Are y'all just chicken? Or... well, this was 7 for a meter, for a square meter. So for a square meter, right, right? But there's 10,000 square centimeters in that square meter, so each one of those is only giving me 1/10,000th of this. What's a 10,000th of 10 to the 7? 10 to the... okay, what power of 10 is 10,000? 10 to the... okay, what power of 10 is 1,000? 3. What power of 10 is 10,000? 4. So if I divide 10 to the 7th by 10 to the 4, what do I freaking get? 10 to the 3rd. Yes. Y'all really need to practice this, right? 10 to the 3rd watts per square centimeter, okay? So that's like, about 6-ish kilowatts per square centimeter. So the sun's given off, right, 6.316, shut up, 6 kilowatts per square centimeter of its surface. What is a household item that gives off a power of about 1,500 watts? I can think of 2 good examples of things that are about 1,500 watts. You know what? I'm all about the coif, and so I need this appliance, which is a what? Hair dryers. Electric hair blow dryers are about 1,500 watts. So are space heaters. Space heaters are typically 1,500 watts. So in other words, in very scientific units, the sun's flux is about 4 blow dryers per square centimeter. And you laugh, but I'm serious. In other words, you should think of things like this. Think in these kinds of terms. The sun's about 4 space heaters or 4 blow dryers per square centimeter is the amount of energy it's given off. And it's got a lot of freaking square centimeters, right? And so it's giving off a lot of energy. But that's, you know, like something to have in your head there. The sun's surface flux is around about 4 blow dryers or 4 space heaters per square centimeter. Relatable, right? I mean, how much is that? I don't know, but I can do 4 blow dryers for every square centimeter. So again, it's funny, but I mean it. I mean it. I'm trying to make things relatable to myself, and that's why I come up with things like this. And I encourage you to do the same thing. It's fun, it's entertaining, and it makes it more real, essentially. Okay? Now, yeah, I'll pause here and say, okay, so here's something where I can't make this real, which is, and apparently, so Veritasium has this video. Y'all know Veritasium? Yeah. Have you seen his one about supernovae? Oh, you got to watch that one. He had one about supernovae, and I think he got this from, I think his name was Russell Monroe. You know who? XKCD? What is it? Randall Monroe? Randall, yeah, Randall, right. What's his last name?
Monroe.
Yeah, Randall Monroe. Okay, yeah, XKCD did this calculation. Okay, so supernova, a massive star supernova, can give off much more energy than the sun does in its entire 10 billion year main sequence lifetime. The sun will never go supernova, but suppose that you had a supernova blow up the same distance from us that the sun is, 1 AU, okay? What would that be like? And the answer that Randall Monroe came up with is, put your nose on I think it's a 1 megaton, 10 megaton, I gotta look, nuclear bomb, and blow it up in your face, and the supernova is like 1 billion times brighter than that, if it blew up where the sun is. I should have looked that up beforehand, but it's about like that. I can't make that relatable, right? Wow, that's big. What would that be? What would that be like? It wouldn't be like anything, right? You wouldn't even be able to experience it, right? You just hit the button and you don't last long enough to even experience it, right? So I can't make that too relatable. I can just be like, holy freaking cow. But I can make this relatable. Now, would I want to be on a surface where every square centimeter is 4 blow dryers? No, I would quickly vaporize. Yeah, hold a blow dryer right up to your skin, and you'll be like, this isn't a good idea. I should probably stop this, right? And so every square centimeter of the sun is like, this is a terrible idea. I should probably stop this, except you'll just vaporize as you're thinking that, if you're even thinking, well, no, it would hurt too much. Don't do it, right? But still, relatable, right? A number that you can kind of make sense of. And so, there you have it. And I guess it's time to go. So, tell your parents. That's right, that's right. What did you learn today? I learned that the sun is 4 blow dryers per square centimeter of power that it's sending out. Yes?
That's